All right, so here we are at ML 129, and here we just get to see how you create these vector representations of words and how those vectors actually capture the meaning of the words or the relative meaning of the words. So this is going to import the pre-trained BERT token model. BERT is a bidirectional encoding scheme, so it considers a word in context from both the right and the left. And so here it is downloading that stuff. And there was a sentence. Here's just an example of the vocabulary. I just printed 20 of the vocabulary words. BERT has a vocabulary of something like 30,000 words, sort of like an average American English speaker. And here's some of those words. And all right, so BERT understands the mathematical representation of those words. So now we're going to take a sentence. Now here's a sentence carefully designed to use the word bank 3 times. After stealing money from the bank vault, the bank robber was seen fishing on the Mississippi River bank. And the point here is the word bank appears 3 times. This refers to a house with money in it, and this also refers to a house with money in it, but this refers to the dirt by the side of a river, which has nothing to do with the previous meaning. So if you just tokenize these, that's the first step, is to convert those to numbers so the large language model can work on them. Now, tokenizing just does tokenize in this simple system. It just tokenizes each word one by one. And as you can see, the word bank turns into 2924 every time. Even this one with a different meaning, because this does not know anything about sentence structure or context. It just encodes each word and other things like periods and commas. And everything starts with a CLS mark to indicate the start of a sentence and SEP to indicate the end of a sentence. So that's tokenizing, which does not yet include meaning. And embedding is what adds the relative meaning of words. Now remember, large language models do not know what the meaning of any of the words are, because it doesn't have any sensory experience or knowledge that there is a world out there. It's just solving a math problem, but it does know a relative meaning. It understands what words should be near to each other in sentences. And that's what this pre-trained model has. So it has to download a model and run it, and it gets 12 layers of responses, and it's going to calculate some of the intermediate things. It's going to show us all the 13 layers of processing, encoding these tokens, each embedded into a vector in a 768 dimensional space. That's what's going on here. And now you can see the vectors with which it has recorded the relative significance of these words. So that's here. All right, and so what is printed, there's 768 numbers in each line. We only printed out the first 5 so you can get an idea. And so here's the start of a sentence marker. So here's the first occurrence of the word bank. And you can see it starts with 3 and then -3 and -1.5 are the first few numbers here. Here's the next occurrence of the word bank. And this is close to 3, -3, and -1 again, because this is also means a house full of money. But this bank down here, instead of being 3 -3, 1, is 1.5 -1 -0.5, completely different. And that's what I mean. This vector has encoded the fact that this word has a very different meaning than that word. Even though it's the same token and the same word, this now includes the context, and from the context you can tell that that has a totally different meaning. And now you can play a few games to see these things compared. You can now calculate the cosine between the angle of vectors to compare them. And you'll see this one here, the 2 bank words that are similar have a 94% similarity, but the 2 different meanings of bank only have a 69% similarity. So that's one way to measure them, whether the vectors point in the same direction. And then there are some challenges where you can take the word boy and compare it to man, and take the word girl and compare it to woman. And the vector difference that takes you from the boy vector to the man vector is very similar to the vector difference that takes you from the girl vector to the woman vector, as you might expect. And down here, there's one where you find synonyms. So there's a word here called monitor, and you can compare that to each of these other words to see how close they are and find the closest synonym to monitor in this system. And in this case, I was surprised that it was camera. I thought monitor would be closest to display because I guess I think about computer hardware, but Bert considers camera.
Sam, are you sharing the screen?
Yes, I thought. Yes, I should be. You folks see it?
Yes, we do.
Yeah, we can see it.
Okay. Okay,
Yes.
good. Yeah. All right. Anyway, that's what I wanted to show you. I'm going to stop this video and